Hi everybody, here is a system of two blocks and we hit these two blocks with a hammer and the small blocks still have a velocity, so it gets free falls. Now if in this whole simulation, after getting the free fall of smaller block, these both blocks have got the velocity is equals to v naught and let the length of bigger block be L. So we need to find the time elapsed from hitting to start getting free fall of smaller block, and let the mass of smaller block be small m and let the mass of bigger block be capital M. And note that the friction coefficient between smaller and bigger block is mu by 2 and between table and bigger block is mu, and consider smaller block as a pointed mass. So please give your trial to this question and keep watching for the solution. Now the key concept is visualize the coefficient in the similar way we visualize friction. So after hitting with the hammer, these both blocks have got the velocity is equals to v naught, and if we magnify here by seeing what happens, so here's a magnifying glass and we can see what happens here. So here are the grooves of small mass because it is a rough surface, and lower it as we have the capital M mass which also have grooves. Obviously it is a frictional surface, and after hitting these both blocks have got the velocity is equals to v naught. So if they are more moving with v naught, then these grooves have not to be hit each other, which is a basic term for making the friction. But this is not happening here. Let's see what is the obvious reason so that this M mass is fall from the capital bigger M mass. Now for understanding that, we see the lower part of capital M mass, so we have also grooves here and also the grooves of surface, and because the surface is not moving, so M is getting little bit slower because of the friction between floor and capital M mass. Because of that, the grooves of smaller M mass get hits the grooves of capital M mass, and from this the small m mass started feeling friction. This is the main reason that m is getting little bit slower, but the rate of deceleration of m is higher than the rate of deceleration of m. Now the friction coefficient between m and floor is mu, and the friction coefficient between small m and the capital M is mu by 2. So from this equation we can say the rate of deceleration of m is slower than the rate of deceleration of capital M. So from this we can say the small m mass is pulling the capital M mass because the rate of deceleration of m is lower than the rate of deceleration of capital M, and this is a reason for that, which is the friction and normal forces. And the second point is from the frame of reference of capital M mass. So if you sit on the capital M mass, you are able to see the M mass is moving with some relative velocity, and the distance covered by M mass depends upon this relative velocity. Let's call this relative velocity be Vm minus m. So this is equals to velocity of m, let's say this Vm, and the velocity of capital M, let's say this V capital M. And the third point is initially the relative velocity of m with respect to capital M is 0, because if you sit on the capital M mass and you are able to see initially that both masses are moving with same velocity, which is v naught, so obviously the initial relative velocity is 0. Now the fourth point is relative deceleration rate. Now because both masses are moving with some deceleration rate, so from the frame of reference of capital M we had some deceleration on small m. So the let's say this relative deceleration rate be a small m minus capital M, which is equal to acceleration of m minus acceleration of capital M, and acceleration of small m is obviously negative 3g mu by 2, and the acceleration of capital M is little bit tricky. So it is negative g mu times m plus 1 by m. That is quite obvious, and we are adding here mg mu by 2m because we know that the small m mass is have some higher velocity, So it hits the grooves of capital M and started feeling friction, and from the frame of reference of small m, it is pulling the capital M mass. So we are adding here mg mu by 2, which is the force exerted by m small m on capital M, and we are dividing this by m because acceleration is equals to force by mass. So from this 4 points we are able to use Newton's equations, which is v square is equals to u square plus 2as. Let's call the relative deceleration is equals to v. So we have v square is equals to 0 square because initial relative velocity is 0, which is our third point, plus 2 times relative deceleration, which is our fourth point, times the distance covered by small m and this L here. So we have v is equals to under root 2 times relative deceleration times L, and we know that v is equals to u plus at, and putting the value of v and all other values, so we have this, and we know that a small m minus m is equals to negative g mu by 2 minus negative g mu times m plus small m divided by m plus mg mu by 2 by small m, sorry capital M it is. So we have relative deceleration is equals to this, we write this in the corner and putting the values, so we get t is equal to under root 4 ml divided by g mu times capital M plus small m, and that is our correct answer. And this answer is quite interesting because if you see all the variables in the answer, you see the capital M mass is here and the length of capital M mass is also here, and we have frictional coefficients also here, and we have gravity, it is obvious, and the small m mass is here, but we don't have the velocity given by the hammer to the blocks, and this is really quite interesting.